So all this we are introducing notations, and yet again for each partial transformation alpha of the set X, we can define relation kernel of alpha on the domain of alpha. So this actually relation is defined on the domain of alpha, and it is defined in this way. So kernel alpha is the set of all ordered pair X, Y, meaning X will be related to Y, X and Y coming from the domain of alpha, if and only if X alpha is equal to Y alpha. So this is a kind of saying two elements are related if they have the same image. So by the very definition of this kernel of alpha, it is then entirely not difficult to check that this kernel of alpha is an equivalence relation, meaning it's a relation that is reflexive, symmetric, and transitive, and that the kernel classes correspond to the blocks of alpha. Because you remember we define a block of alpha is the group of elements that map to the same image, and you now say that X and Y are related if they have the same image. So that means the equivalent class of a particular X will be exactly the block where that element belongs. So this is yet again another perspective of looking at the blocks of alpha. So those blocks of alpha that we defined in the previous slides are exactly the kernel equivalent classes here, and this relation is an equivalence relation. It's not difficult to see because every element has the same image as itself, and if X has the same image as Y, then with Y, then Y is also having the same image with as X. And then if X and Y have the same image and Y and Z have the same image, then X and Z is also having the same image. So it's not a difficult exercise to check that this particular relation here, kernel of alpha, is an equivalence relation. It partition the domain of the map, and this partition constitutes precisely of the kernel block of alpha. I give you an example here. If you take a set X of 12 elements, 1, 2, 3 to 12, and consider this partial transformation. This is a partial transformation on the set X of 12 elements. But then it's a partial transformation because it's not a mapping from X to itself, but it is a mapping from a subset of X to itself, because as you can see, if you scan through the images here, you can see that 10 is not appearing anywhere. So it's a strictly partial transformation. But then we have a block of element 1, 3, 4 that is mapped to 3, and 2, 5 mapped to 6, 5, and 6, 8, 11 mapping to 2, 9, and 12 is mapping to 9. So this is a partial transformation. This is the notation we introduced. This is our A1 mapped to B1, A2 to B2, A3 to B3, and A4 to B4. It's a partial transformation. The image set is 2, 3, 5, 6. Actually, the set of this element over here. These are the images. You can see them. So 2, 3, 5, and 9. Okay, 6, 9, and not 6. And we can see that the kernel classes, because if you are talking about elements that are mapped to 3, these are them, and these are the elements that will be related to each other under kernel relation here. So the kernel blocks are 1, 3, 4, 2, 5, 6, 8, 11, 9, and 12. These are exactly the blocks of alpha here. So this is how we define it. So so now we talk about how we can compose two partial transformations, because our target is to make the set of all partial transformation into a semigroup. So we require a binary operation, and we will need the binary operation to be an associative operation on the collection of all binary of all partial transformation. So given two partial transformation alpha and beta, the composite, that is the product of alpha and beta, is again another partial transformation defined in the following way. So we choose from among all the partial transformations of the set X, we choose one that is going to satisfy the properties which I'm about to mention. to be called the composite of alpha and beta. So the composite of alpha and beta should have as its domain the pre-images or alpha inverse images of the intersection of Im alpha and the domain of alpha. And then the image of this composite should be the image of the intersection of dom beta with Im alpha. And then you now define how this mapping, so you have identified a domain and you also identify an image set, and then you want to assign members from here into this particular set. And how would you do the assignment? The assignment is done in this way. And what you want to consider, if you take any element from the domain here, then that element is a pre-image of the intersection of the image of alpha and the domain of beta. So actually it means it's an element in the domain of alpha because it belongs to the image of alpha, and so up there, so it is a pre-image of some image of alpha. So actually it is in the domain of alpha, so you can speak of X alpha. So this X alpha is defined because of the choice of the domain over here. So this X alpha is well defined and it is an element in the image of alpha, and because X alpha is in the image of alpha now, and the domain is actually taken in the intersection. So this particular X alpha belongs to the domain of beta because you are taking an intersection over here. So therefore beta apply to it. So beta will apply to any element that belongs to the domain, and once you do, you fall in this particular set Im alpha beta. I try to give you a visual of what is going on. So imagine you have the domain of alpha, and because it's a subset of X, and alpha is going to map it to another subset of X, which is the image of alpha. So every element here will be mapped to some element in here, by alpha. And beta will have its domain, again, a subset of X. So the two will intersect. They may either intersect or the intersection can be empty, but it's still an intersection because there is no restriction that this intersection must be must be a non-empty intersection. So once you have this intersection, every element in the intersection here will have a pre-image. So, and beta is going to map this portion, its domain, to the image of beta. But if you pick an element in the intersection here, it is already an image of element in X. So every element here is X alpha, and that X is coming from the domain of alpha. It is sent to X alpha by alpha, but being in the domain of beta will also be mapped to some element in here. But then now what you do is to look at this particular intersection, and you look at all the pre-images of this that intersection, and now alpha will send members of this portion of its domain to this intersection, and this intersection will be taken to beta by beta to a portion here inside the image of beta. So therefore you call this the domain of alpha, and this portion here is called the domain of the here. You call it the domain of the composite, and this is now the image of the composite. And once you do this, you can see that composite is always defined only on this portion of the domain of alpha, and this will be the image of that composite. So this is how we define composition of alpha and beta in partial transformation, because if you are outside this portion, the mapping will not be defined. If you take some y here, alpha will send it outside here, and this particular element is not inside the domain of beta, so beta will have no effect on it. So therefore you cannot be able to perform the composition if you look outside of this portion, and that is why this is the identified portion that constitutes of the domain of the composite. So this is how we define composition. Now we form a set because we have a way of multiplying two partial transformation to get another partial transformation. So we now denote by Px the set of all partial transformation. Set of all partial transformation. This should be partial and not full here. So the set of all partial transformation is denoted by Px of a set X, and it is a semigroup under the composition which we have just described. So I will leave it as an exercise to prove that this binary operation is actually, from what we have described, the binary operation is clearly closed and well defined, but then we still need to show that it is associative for us to claim that this set is a semigroup. But then it will be associative, and we are going to prove it in a later part, maybe in the second chapter of the course. So now if you take the collection of full transformation, that is mappings whose domain is the entire set X and denoted by Tx, then this Tx is a sub-semigroup of Px, of the semigroup Px. This semigroup Px is called the partial transformation semigroup, and the sub-semigroup Tx is called the full transformation semigroup on X. Well, the proof is not difficult because we only need to show that the domain of the composite of any two full transformation is X. And so if you go by the definition of the domain in the previous slides, we can now see that if you take two maps, alpha and beta, from the full transformation, the collection of all full transformation, then the domain by the formula or the definition of the domain of the composite, this will be the alpha inverse of the intersection of Im alpha with domain of beta. But since beta is a full transformation, this domain is X. So we are intersecting X with a subset of X. So this will be the subset of X Im alpha. And then in alpha inverse, this is exactly X. So therefore the domain of the composite of any two full transformation is still a full transformation. So therefore the composition is closed in this particular collection of all full transformations. So therefore it is a sub-semigroup of Px called the full transformation semigroup. So we have a special semigroup consisting of all full transformations. Now this semigroup has a universal property. It has a universal property in the sense that every semigroup, you remember in group theory, the symmetric group is having this property that every group is isomorphic to a group of permutations, or symmetric group, a subgroup of the symmetric group. So something similar happens with the transformation with semigroup. In semigroup theory, if you take any semigroup whatsoever, then there exists a set X such that the semigroup can be embedded in the full transformation semigroup. So this is how it is happening. You have a semigroup given, and then out there you can always find a set X so that the entire full transformation semigroup will contain an isomorphic copy. So there will be a copy of S inside here, and then which means every element here can be identified with an element in this portion of the full transformation semigroup via an injective homomorphism. And so we have an embedding. An embedding is nothing but an injective homomorphism from a particular semigroup into some other semigroup. So this is how you describe this universal property.